So the great emptiness is waiting for Professor Snorre Christiansen this evening. We spend our time here at the Taiji Centre working with the relaxation of the mind, the openness of the human spirit and the heart. And no small task in this day and age. And indeed, it's a very warm welcome to you all if you're arriving for the very first time in this vicinity this evening. Very warm welcome. It gives me great honor to hold this emptiness for the most special people, which of course is all of you, but especially this evening, to honor, celebrate, how can I say it? A friend has come this evening with this honor of giving his book out on mathematics. What is that? I think it's something to do with emptiness, zero, and the fulfillment of everything that is. How to calculate the daily breath in one lifespan is what I'm interested in. And of course most of the people that come here has touched on this idea of emptiness and how to be in a natural state of mind. So the last thing on my mind when I think of that is mathematics. So how on earth did I become so good friends with Professor Snorre Christiansen? So through this friendship and through the study of Tai Chi, we have learned to understand that there is some level of embodiment to do with how the universe is demonstrating itself to us every day and how we demonstrate ourselves to one another. And so this catalyzation, as it were, of Snorre being here this evening with his friends, his family, and his students, joining with mine, is very profound, very poignant. Especially as I was with my family in the Museum of Science in London yesterday. Such a coincidence, such is my life. So I walked through the Department of Mathematics. So I think I'm ready for you. Very much so. So very warm welcome, Snorre. This is a great honor for me to present the open space and also the Mathematics Fundament, Spiel i Grenseland. Take it away.
Thank you so much, Pamela, for bringing the book into existence with this sound, which comes from some time immemorial. And I'm very honored that you express your friendship. And if I may, I want to say something a little more, that I feel that ever since the day, 9.5 years ago, when I first came into this truly wonderful space, I feel it has been a romance. It has been a romance through the silence of our practice, through your gentle teasing with my job title, with your strict corrections on my posture, and also for this evening, I want to bring out one more aspect, and that is that you have always had a very creative language with which you talk to all of us, but you talk to me as well. And this quest for a language, for precision, for finding the creative words to somehow create action. In this space, I feel there is room for mathematics, and you have always expressed your conviction of that fact too. So in this we have been united, and it has been a blessing for me to meet you. So yes, I want to thank other people also on this occasion. I want to thank Lars for joining me in this event. Lars is a multi-talented guy in music, in Aikido, and also in mathematics and Tai Chi, and that's how we have met. And we have had many conversations about the nature of mathematics, what it could be, the relation to Tai Chi. Are these complete opposites? Are they on a profounder level maybe equal in the quest for emptiness that you mentioned, and what can this emptiness nurture, in fact? So I hope we'll be able to touch upon on these subjects. I want to thank all my friends, family, and students who have come here. I'm very delighted that you discover the Taiji Centre, which has meant so much to me. And finally, 9.5 years ago, I entered this room, but that's also about the time when me and Kristin proposed a book which has now materialized after talking and talking and talking. So this has been a long process, and I'm very grateful to Kristin for all her contributions there. So yeah, I have colleagues here as well, so I'm going to speak to both mathematicians and non-mathematicians. It's a bit of a challenge for me. I think it's hard enough to talk about mathematics even with mathematicians. What is math? What is math? So maybe I can give an introduction to the book while I'm standing here. So yeah, Matematisk Fundament, looking like this.
Spot the difference.
So as Pamela told me a few days ago, you can actually judge a book by its cover. And I did have a word to say about the cover initially, but then I left over to the publisher, and it turned out like this. And I'm very happy that a certain expression about the origin and the mystery of mathematics appears in this cover. So yes, I want to connect with Tai Chi, and then perhaps our fundamental practice in Tai Chi when we start is the position of Wu Chi, of a neutral emptiness. Neutral emptiness. And take time to absorb that neutral emptiness and feel into it. And my overarching principle with this book has been that at one point in a mathematical career, one should forget everything one knows. One should empty the mind. And what does it mean to empty the mind? How much are you ready to empty of your mind? So that's the question. So the book really starts at that point. That's the point of departure. And then, as such, it should be hopefully of interest to a large audience. but it's also a textbook. So if there are people from the department here, I want to reassure them that it's not only an experiment in diving into the Tai Chi, it's also a textbook in a very ordinary sense. So it's a textbook in the sense that Kristin and I proposed a certain curriculum back then. This was sent to the department. Other people, I think, must have had similar ideas. Anyway, it was agreed that we have a course, and this course has been taught over a number of years. And out of this process of teaching a course, the curriculum has solidified in this book. So it's a textbook in the sense that I follow usual conventions. I haven't tried to be too original. I do mathematics the standard way, but there are some originalities. I have included some poems, and also I have included a rather long introduction. It's very strange that in mathematics books there is no introduction usually. The introduction usually consists in saying, well, for the second edition, I have added a chapter on this or that topic, and that's it. So I took the time, and I felt the need, and I felt the hunger for writing something about what mathematics is all about, and that's what I hope will appeal to not just students. I want to thank my Tai Chi friends for having supported me this year, for having been curious about many of the topics of the book. Like what do mathematicians mean by infinity? What role does contradiction play in mathematics? And I want to thank also my Tai Chi friends for supporting me in having the poems in the book. It was not obvious. The publisher wasn't enthusiastic, but yeah, maybe you will not be enthusiastic either. But anyway, now I am a published poet. That was my secret goal of all this. So yeah, what is mathematics? We can I've tried to find out what mathematicians have to say about this question, and it's remarkably little. There is a famous book from 1940 called "What is Mathematics?" And it starts by saying, more or less, that it will not give a definition. It will just give examples of mathematics, and it will not say what the nature is. So what is the nature of mathematics? I'm very happy that we have music with us today. I want to stretch the story I want to tell back to the Pythagoreans, the school of Pythagoras. And to the school of Pythagoras, mathematics had 4 components. It was number theory, geometry, music, and astronomy. Music was part of mathematics. Pythagoras is supposed to have said there is music in the spacing of the spheres, there is geometry in the humming of the strings. So the spacing of the spheres in this context are the celestial spheres on which it was believed that the planets evolve. So this worldview, which placed mathematics almost at the top, crystallized in the deep belief that the purpose of mathematics was to introduce to the divine harmony. The divine harmony was the purpose of mathematics, and it was approached through number theory, geometry, music, and astronomy. So, I don't know, I'm going about my rant here. Should we just continue like that, or do we want to have a dialogue, or?
Let's continue.
Yeah? Okay, so that was Pythagoras and his followers. And I want to compare this belief in the divine harmony with how mathematicians talk about mathematics today. So if we ask mathematicians today, why do they do math? Can you guess what it is, perhaps? Well, the two main reasons are because it's beautiful and because it's fun. Fun and beautiful. And this is quite something. Fun and beautiful. It's not nothing. It's used to attract students, and so fun and beautiful. Fun and beautiful. And then a definition of mathematics that has started to become popular is that it's the science of patterns. That we somehow see patterns everywhere, and we systematize them and make a theory around them. And patterns here is understood on several levels, I think. There is one, you perceive, for instance, repetitions in tilings, and this has a certain structure, mathematical structure, that you identify. Or, in this context, one would say that the laws of nature, as they appear in physics or in, maybe in social sciences, are examples of patterns. So my little point of amusement is that we have gone from divine harmony, that the purpose was divine harmony. We have gone from there to funny patterns. Funny patterns. And maybe it's a sign of humility, I don't know, but I think something has gotten lost along the way. Something has, and one way of phrasing what is lost in this definition, and which would not be controversial, is to say that there's something about the big picture that has disappeared. So how is this big picture perceived through the ages? One way of describing the activity of a mathematician is to say that we prove theorems. So a theorem is a statement that we know to be true. And the reason we know it to be true is that we're able to prove it. And the meaning of the word theorem is actually an object of contemplation. The origin is object of contemplation. So theorem comes from the same word as a theory. And ultimately it comes from theos, which is Greek for God. So the theorem that we are considering derived from God in the sense that it's something we contemplate. And the reason we have something to contemplate is that we have an aspect of God. Okay. This is even more interesting than that, because on the way from theos, the Greek for God, to theorem, as we use it in mathematics, the etymology went via thea. And thea means goddess. So the etymology went via the feminine before reaching mathematics. And the feminine thea means goddess and implies the sight, the divine sight. So it's something that is revealed to you, like a goddess in the forest, something. So that's the meaning. That's the meaning of the word theorem. So mathematicians can relate to still the etymology of the word, and in this way connect with the divine. And I said that this etymology suggests something about vision, that the theorem is something you see. But as we approach it, it's something we prove. So the proof, what is a proof in mathematics? A proof in mathematics is a text consisting of assertions where we have agreed beforehand what is allowed to be deduced from the preceding assertions. So we start from certain assumed assertions, and we allow ourselves certain deductions. So the rules of proving, that's logic. So we have now a certain conjunction of sight and language. Sight and language. So that's, I would say that's the fundamental conjunction in mathematics. There is a certain aspect of the divine you're contemplating, and you approach it through a language. And this conjunction that we have in mathematics is of universal value, I could say. So the etymology for logic is logos. Logos meaning reason, or you can stretch it to some divine intelligence or universal intelligence. And so I just want to say something about the conjunction of theos and logos here. Theos and logos appears in the Gospel of John, the first line. In the beginning was the Word was with God, and the Word was God. So word in this text is a translation for logos, and God is a translation for theos. So in the beginning was the logos was with God, with theos, and the logos was theos. So you have at the core of our civilization really the meeting of the Christian and Greek traditions. You have the conjunction of the theos and logos, which is the basis of mathematics, I would say. Okay. That was my introductory speech. So this has been a source of inspiration for me. But I have another source of inspiration, which has been Lao Tzu. And I worked a bit on translating Lao Tzu into Norwegian. And this also will say something about mathematics. And this is in Norwegian. Veien som veilegges ikke den endelige vei. Navnet som nevnes ikke det endelige navn. Stillhet opphav til himmel og jord. Kall mor til multiplisitet. I null ser vi unnfangelse. I én ser vi fullbyrdelse. Disse to, samme kilde, kallet med ulike navn. Sammen kaller vi dem mørke. I mørkere mørkhet unnfanges uendelighetene. Okay, then I would like to invite Lars to
Actually, I thought you let me off the hook now.
Okay, it's not that easy. Okay.
Yeah, so my introductions will be very, very short. It will consist of thanking you wholeheartedly for this great honor, actually, I have to say, without the, how do you say, tiniest little bit of sarcasm, which I use too much. I'm very honored that you invited me to join you for this book launch, I think is how they say it in English. And I've been really excited to take part in this. So I'm a student of Snorre, and I'm a student of Pamela, and I'm a student of music, and so Snorre has invited me to be an interlocutor partner for this happening.
With all your different hats, I thought you were the perfect bridge builder here. So I'm very happy that you.
Yes, so actually I was wondering why he asked me, because I am not a great mathematician. I studied some mathematics. Snorre called me a dilettante. I think it was in the loving fashion, but and I kind of, after having thought about it, I realized that yes, maybe I am, but I know certain things. So, but I also know what it is not to know so much of mathematics. And so this is a thing, maybe. Because this book is talking about the fundamentals of mathematics. And to people who don't know very much of mathematics, I guess maybe that is arithmetic, like 2 plus 2, 4 times 8. But the fundamentals of mathematics are something quite different. You talked a little bit about the theorems.
Yeah, I talked about theorems. I thought, okay, as a first approximation, this is a accurate statement of what we mathematicians do. But there is also the part where we define objects, and that should not be forgotten. So yeah, we have this capacity of defining objects, and it's almost like bringing these objects into existence by the act of defining them. I think that's it's a mysterious fact of mathematics, actually, that we almost create things out of nothing.
How?
Yeah. Yeah. So I would have liked mathematics to really come out of nothing, and I have had that hope, but the closest I came to this was to give mathematics a room within language. So the book starts with logic. That's really that's the basis on which we build. So we clarify the language we allow ourselves to use. We really restrict the possibilities, and this somehow increases our power. It increases the reach of our arguments.
But so when common people say that this is logical, they actually mean this is common sense. I understand it. But when you say we start with logic, clearly you mean formal logic. But there are various kinds of logical systems that we can build. So why do we choose this exact system?
Yes. So I'll get back to that. But I want to tell. I want to relate to Arne Næss. I want to relate to Arne Næss because on the one hand, he was the patron of this center, of the Taiji Centre. And on the other hand, he was responsible for the main course in logic, you can say, at the University of Oslo. So in the 40s and 50s, he identified the need for all the students to have a common understanding of how language works. And he did consider teaching what you call formal logics in this examen philosophicum. He decided not to do that. He decided to teach the logic needed for debating and for clarifying concepts, which was of more universal nature, and or more universal need, you can say. So for a very long time, that's how the students at the University of Oslo learned about logic. For some reason, this was discontinued. So it was no longer part of the common curriculum to learn the rules of how you build sentences and deduce sentences. And this was a great loss for mathematicians, of course. Where were we supposed to learn these things? So I think that decision back then were among the factors that contributed to the necessity of having this book. The rules of logic are not that complicated, but you cannot invent them. You cannot just invent them like that. So that's a little historical background on logic at the University of Oslo. And now we got back to your question, which.
My question was, it doesn't have to be exactly that, but the point is that in mathematics we choose a certain logic, which we call classical logic.
Yes.
But there are other kinds of logical systems. And there are even systems that have applications in mathematics and probably in other fields. And I know that certain scientists are investigating whether other systems of logic could be useful, for example, in quantum physics, because the quantum world is really weird. It's not either or. Our logical system is based on this notion of either or. It cannot be both and cannot be neither.
Yeah.
Would you like to elaborate on this?
Yeah, well, it's you're pinpointing a point where I must say I'm very interested in all these other logics. I wish I knew about them. I wish they were part of our curriculum to a greater extent. I'm sad I didn't know about all these other logics, but yeah, the logic that is in the book is the standard logic, and I can't say why this is the one that is accepted or used by 95% of mathematicians. My guess is that it's the simplest, is the clearest, and actually my only approach to the other logics is through the classical logic. So I would use the classical logic as a point of departure to describe these other ways of using language, where you might have fewer possibilities for deducing things, for instance, or that the conjunction of two propositions is something more complicated than just A and B put next to each other.
So one thing that this logic that we are using in mathematics actually does is that it takes away the possibility of contradiction. Is that not?
So one of the reasons for developing logic so precisely is that the mathematicians are very fond of contradiction. So contradiction is it's not only the salt of life. It's at its origin, I suppose, we were more interested in contradicting somebody else. But as mathematicians, our arguments are we're not contradicting ourselves. It's not the purpose. But we have what we call proofs by contradiction, which is one of the most important rules in or principles in mathematics. Proof by contradiction. And a proof by contradiction works as follows. If you have a hypothesis or a premise and you can deduce from this hypothesis a contradiction, then you know that your premise is false. And this looks reasonable enough, but it creates difficulties for language. And the difficulty is that in natural language we have contradictions. And even some of our most cherished wisdoms are contradictions. For instance, Niels Bohr, a famous physicist, one of the fathers of quantum mechanics, says that the opposite of a profound truth is another profound truth. And we want to believe this, but if we take this fact into mathematics, you start with any premise, you do your deduction, and you say, but the opposite of a truth is another truth. I have my contradiction. I have a proof of my of the contradiction of my premise. So,
but he was a quantum physicist, so
he had a different logic. Yeah.
So that's interesting. So you're saying in natural language we can have like a double negation, and we don't end up where we started. So
that's also part of the game. Yes.
You say something. You have a sentence in your book, which is you remember.
Well, if I say, I don't disagree with you, it usually means but, comma, ba, ba, ba.
It doesn't mean I agree with you.
No.
Like if that would be a logical statement in mathematics, it would mean I agree with you.
Yeah.
Because it's double negation.
Yeah. Yeah.
But that's so the natural language works in a different way.
So yeah, the first chapter of the book is to clear up such questions and to point out that in mathematics double negations are precisely equivalent to the statement you start with, assuming classical logic.
Cool.
Yeah, classical logic. Yeah, I can say something about the first one to sort of describe logic was Aristoteles. And Aristoteles wrote down rules for inference, and he came to the conclusion that there were 200 rules for how you can deduce something from something else. 200, or more than 200. So anyway, in the book, it's down to 8 or 10 now. So yeah, that's thanks to the work of logicians from 1850 to 1930. The Aristotelian logic was somehow superseded and formalized, and that's what we still use today. It's classical logic in the sense of Boole from the end of 19th century.
So logic is one of the most fundamental tools of mathematics. Another one is set theory. But even there are prerequisites, or so to say, building blocks that you use, that you need in order to use this logic. And so I want to point in the direction of undefined terms versus defined terms and definitions. Would you like to say something about that?
Yeah. So
why cannot all terms be defined?
Yeah. Why
Wouldn't that
cannot
be
all?
better?
Yeah. What should you? Yeah. The problem is in terms of what do you want to define it, and so can you? If you define it in terms of something else, then you have the new problem of defining that something else.
So it becomes a circular.
It can become circular, or maybe it's an infinite regress. So anyway, the need for undefined terms is sort of implicit already in Euclid. So the Greeks had identified the problem, but they played on both
Sides of the court.
Yeah, on both sides of the court, because they introduce certain concepts, and when you talk about them as undefined terms, you just say what these terms can be used for. So those are axioms. So you don't define your terms, but you say what properties these terms have. And Euclid did precisely that. He writes the axioms for plane geometry. And these axioms are just statements of the form. For instance, point and line are two undefined terms. And given 2 points, there is a unique line going through them. That's an axiom. And you haven't defined either point or line in this context, but you say what the relations between the concepts are. But Euclid, nevertheless, felt the need for a definition. So that's why I say he played on both sides of the court. So he gives the definition that the point is that which has no parts. Nice definition. It doesn't say what the part is, so that's how you get the infinite regress of possibilities.
So it's in order for us to have some common ground before we start this mathematical building project. We want to create some common ground, and one of the ways that we do this is via undefined terms. So we try to choose undefined terms which are as simple as possible. So we try to kind of remove all possibility of misunderstanding. So we say like a point. Okay, that's really simple. I think I know what you're talking about when you're talking about the point. Is that how?
Yeah. So do we know what we're talking about?
Yeah, that's another question.
That's the challenge.
How do we know really?
So I think this setting up the axiomatic system with the basic accepted truths about our undefined terms is our way of coordinating between the two of us what we have in mind when we utter these words.
But this, I mean, maybe we should. This is the point to depart into like deep philosophical question, but maybe it's too early. But anyway, the question kind of pops up, you know, because how does this meaning come up to, you know? Okay, so in mathematics we can use concepts without there being too much meaning to it. Like say we can have a point, we don't need to understand too much about it, maybe, and that can come later, and how points are interrelated and so on. But also in language we have this problem, so to speak, that we speak and we understand each other, but and we can if we have a how do you say that, like a ordbok, we say in Norwegian, I forget, a dictionary, you will see that a certain word is defined by other words, But then, if you really wanted to understand it, you would have to look up in the dictionary the definition of all the other words, and then you have this problem that you just mentioned. So how is this meaning or this coherent understanding created?
So I
Please
wanted
tell
to
us.
know. I wanted to know what the linguist thinks about this. So I bought a book called Meaning, and he said something to the effect that there is no in language there is no exact definition, except perhaps in mathematics. Except perhaps in mathematics.
So now you're saying there isn't one even in mathematics.
So that is the question, because you mentioned these undefined terms, and in the book now we're in chapter 2. We're in chapter 2, 8 to go. In chapter 2 we learn set theory. Set theory is the mathematical theory which puts down in precise terms our intuition of collections of objects. So that's considered more fundamental than numbers today. The concept of collections of objects. We call them sets. And this set is an undefined term, but we say something about what we're allowed to, how we're allowed to manipulate sets. And, I don't remember the exact numbers of assumed truths we have. Maybe it's 13 or so, 13 axioms for a set theory. And this is then as good as a definition. We don't have a definition of set. We refer to collections, but that's a circular argument. But these axioms restrict the possibilities of what the set can be. And that's as close we have to a fundamental object in mathematics. And all the rest of mathematics, according to 98% of mathematicians, will be based on set theory, will be defined in terms of set theory. And we have the impression that our definitions are perfect in this world. So given that we assume sets, we can define things perfectly, and just by uttering the words, so to say.
So I'm just curious, but so we have the undefined terms, and then we have maybe definitions that are based on these undefined terms, or axioms more or less at the same level, perhaps. So axioms are statements that are not proven.
Exact. Yeah.
And on top of that is where we start proving stuff.
Yeah.
So we need all this other stuff that is not really proven. It's just, what is it based on? Is it based on the way that we want things to behave?
So when mathematicians are pushed on what they really believe is the profound nature of their field, it's often described in terms of two philosophies. One is the formalist philosophy, where we say that okay, we don't know what we're talking about, but we have some rules for talking. And so that's the formalist point of view, and we don't talk, we write things on paper, and so we have rules for what we're allowed to write. And then there is the other side called the Platonist view, in reference to the Platonic idea of ideas, which is that mathematics describes abstract objects in some parallel universe to which we have access by reason. So those are the two main philosophies of mathematics, and there are subcategories. But anyway, the mathematician philosopher Reuben Hirsch says the following. He says that mathematicians are Platonists on weekdays and formalists on Sundays. Which I think is funny, because to me it's the exact opposite. To me, I'm formalist during the week. I have certain rules according to which I'm allowed to write my papers. And but if I'm asked about my intuition about these things, I would say that's the Platonist view that there are these mathematical objects that we somehow have access to.
So around the turn of the last century, some mathematicians were trying to create a waterproof, fundamental, the fundamental building blocks of mathematics through set theory, amongst others.
Yeah.
And they encountered some problems.
Yeah. So this is called the crisis in the foundations, and the problem was mathematicians wanted to talk about the infinite. Since Aristoteles, actualized infinites were considered suspicious because of paradoxes like Zeno's paradoxes. And this view lasted well into the 19th century, and great mathematicians said that there is no infinite, there is potential infinite, meaning that there are things that are bigger and bigger, but you can never consider the totality of these big things as one infinite object. But then came Cantor and tried to formalize infinities in mathematics, and this created the whole new possibilities for proofs. Whole new possibilities for proofs. For instance, Hilbert was a great mathematician. He gave a new proof that a certain mathematical object exists, but he never described this object. He never showed how to compute it. He just proved that it exists, and this proof was of the type that if it didn't exist, he would deduce a contradiction. So it's a proof by contradiction of the existence of an object. And this was very new at the time, and mathematicians from the old school commented that this is not mathematics, this is theology. But it so turns out that many, most mathematicians really liked these new methods of proof and wanted to have set theory as a tool for doing mathematics. And the problem was, after a while, they found out that the theory was self-contradictory.
In what way?
In what way? Well, in what way was it self-contradictory?
You're talking about Russell's paradox, or?
Yes, indeed. Well, it's contradictory in the sense that using the axioms of the theory, you could prove that a certain object exists, which is a member of itself, if and only if it's not a member of itself. And this is an impossibility. So this was a shock to the mathematicians and a challenge, and they started to doubt the foundations of mathematics. And so there was a huge work of redoing the foundations in the period 1870 to 1930.
There's something about objects referring to themselves, self-referentiality, and negation that usually seem to create these problems. You have the famous old Greek Lars paradox, which is kind of a version of the same, or at least using the same, the self-referential and negation. Would you like to say something about that?
Okay, yeah. So in natural language, I gave some examples of contradictions. So one of the oldest contradictions pointed out by the Greeks was the paradox of the liar. So if a person says, "I am lying," is he then telling the truth, or is he lying?
It's
Good
useful.
question. Very good question. Yeah, it's a good way of getting out of difficult administrative situations. So anyway, you have to rebuild the language of mathematics in such a way that such sentences do not exist. And one way of excluding this kind of sentences is to not allow sentences that talk about themselves, which are called self-referential sentences. But you can make more elaborate contradiction by having two sentences, and one sentence talks about the other one, and the next one talks about the first one, and then you're in the same trouble again. And so the way out of this was first proposed by Russell and Whitehead, which invented something called theory of types, and that's a ridiculous book. I have to say. Anyway, so yeah, one wants to keep as much as possible of the natural language and not invent a whole new mathematical theory with powers of things that are not allowed to talk about each other. So the strength of set theory is really that you get as close as possible to the possibility that the language talks about objects and objects talks about language. You want this is like a fundamental strength of the system, and yet you don't have self-contradictions. Now, we haven't observed self-contradictions for the last 100 years, but we know for sure that we are not able to prove that there are no self-contradictions. So we can't prove that that mathematics is not contradictory.
When you say we can't prove, is it because we tried really hard and we didn't manage, or are there other reasons?
No, this is these are works going back to Gödel, logician, 1930, and this was a shock to the mathematical community, because they had set out to tidy up the foundations of mathematics. And then Gödel, the logician, proved within a certain proof system that for any theory you cannot use the theory to prove its own non-contradiction. Yeah. For certain strong systems. So that was a shock, and this has amused philosophers, and maybe it's among the last mathematical results that really have a philosophical implication. But many mathematicians are a bit tired of discussing Gödel. There's a very nice book called A Very Short Introduction to Mathematics by Timothy Gowers. And he says, I will not talk about Gödel theorems, and I will not talk about fractals. So, yeah.
From an intuitive point of view, which might not be very useful in mathematics, but it kind of seems that these results by Gödel and these contradictions that pop up when you use self-referential systems, they say something about limitations of logics on like saying everything about something. But you can say a lot of stuff that you say is true because it is true within your system, but there is stuff that you cannot say things about. And if we go back to the Greeks again, because they were really eager to use mathematics to say things about existence and universe and music, and like you were saying in your introduction, does this mean that they were wrong, that mathematics is actually not a tool that can give us knowledge about the universe in its completion?
Well, Gödel's theorems are based on a certain view of logic, and my hope is that this view will be superseded. But I mean, I don't know the formal details. Gödel's theorems are it's not one of those fancy logics that you mentioned of quantum logic or other logics. Yeah, we're over in the topic of mathematics as a language for modeling, and then yeah.
We're off topic, you're saying?
No, fine. Let's talk about that also.
But so this, do you want to say something more?
Yeah. Because I have great admiration for the Pythagoreans, but I have a little story to tell, and the Pythagoreans were extremely fascinated by numbers, and one of their favorite numbers was the tetrakis. The tetrakis is 10, and the reason it's tetrakis is tetra is 4, and 1 plus 2 plus 3 plus 4, that's 10. So the Pythagoreans were so in love with this number that they wanted to see it everywhere. In particular, in astronomy. So they were convinced that the universe consisted of 10 objects. So we want to make this work. So let's count the objects we have in the celestial spheres. So we have Mars and Venus, the two inner planets. Then we have Mars, Jupiter, and Saturn, outer planets. Now we're at 5. So we can add Earth, that's 6. The Moon, 7, and the Sun, 8. But this doesn't add up to 10. So how do we get 10? Well, the Pythagoreans were convinced that there was also a central fire in the universe. And that somehow we couldn't see the central fire because there was a 10th planet that obstructed the view.
Mm-hmm.
So,
are you saying this is far-fetched?
I don't know. I think this is it is perhaps the origin of laws of nature. We have some mathematics here, and we want to fit it with the observed data, and we try as well as we can, and the theory contains many fascinating ideas. The idea of a central fire, I like it very much. But yeah, the Pythagoreans were also into funny patterns as we have today. Funny patterns also.
But this understanding that mathematics is the way to understand the universe is quite predominant also today. I think I can dare to say. And then we have the famous Italian Galileo Galilei, who said, maybe not in these exact words, but that more or less mathematics is the language of nature.
Yeah, he said that the laws of nature are expressed in terms of triangles and spheres, and without knowledge of these geometrical objects, you wander in a labyrinth in the dark. So that was it. Yeah. Okay. I can connect this with. So actually, the way mathematics is taught now at university is that the first year is very preoccupied with teaching calculus, which is the language, as it says, the language for physics and other sciences. So that's the first year, and this book is used for a course in the second year, which is the first course that the mathematicians have without their fellow students from physics and chemistry and natural sciences. So then there is a shift in the meaning of language, because mathematics is taught as the language of science in the first year, but that's the language of calculus as it is used to express laws of nature and deducing consequences. So the way I introduce language in this book is a little bit more in the direction actually of computer science, where language is something within which you can deduce. So it's a logical language where you have deductions. So yeah, there's a little distinction there.
So we are having this encounter in the Taiji Centre. And one could probably say that Tai Chi is another way of coming to know the universe somehow, coming to know yourself in the universe, or this is not a definition, by the way. So, how are they similar? I mean, mathematics and Tai Chi. I'm trying to point in the direction of an embodiment somehow. Or are they similar, or are they completely opposites? Or
yeah, I think along the way we have identified some paradoxes here. The paradox, on the one hand, the way I approached mathematics long ago, I did math, I forgot my body. It was part of the feeling that my body didn't exist anymore, that I was somehow floating in an abstract space where I could deduce and see things. Okay, and then the book is precisely at that moment in the trajectory of a student where I think you should empty yourself of what you know and recreate everything on a firm basis. But this emptiness that we experience is a rather it becomes, to me at least, a rather bodily experience. And moreover, I have more and more the feeling when I think about my practice as a mathematician that I have a certain intuition for how things fit together in an argument, and this flow feels somehow bodily to me. That there is a certain presence, and that by tapping into the intuitions of the body, I can extend the reaches of my mind somehow.
Have you always had this experience, or is this a result of years and years of working with mathematics?
It has never been a goal of my practice of mathematics. It's more an observation after many years, and I say to my beloved students that they have to know things. They have to know things to the point where it sits in the body. The definitions of mathematics become part of you. That's.
Create a mathematical creature.
Yeah, I think so. Yeah. The mathematical golem. Yeah.
Somehow it's hard to avoid thinking about the fact, or the idea. I wouldn't say fact. The idea that the reason that we can create this artifice of mathematics using a little bit stardust in the beginning, and then we start reproving stuff, is somehow we share common understandings which are not derived from, say, the proofs of mathematics. That's something that is somehow connecting us, and this kind of points to the big question whether mathematics would be the same everywhere. So you have this thought experiment: if there was an alien on some faraway planet that never exists in a completely different form, maybe he has no real physical substance, for example. How would they use mathematics, or what would it look like? Would it be similar to ours? Because it seems like we're choosing somehow, we're choosing the logic, we're choosing the fundamentals, which allow us to create what we are creating, which somehow relate to our understanding. Or am I saying too much?
No, I agree, and I just want to add, I think I went into mathematics with the hope that it would be sort of deprived of the problems with everything human. That it was a world where you could achieve, if not truth, you could achieve at least certainty. And actually now, after 30 years, I have more the feeling that every mathematical concept as we introduce them is somehow tailored to the human mind, that we choose to express things in chunks of language that are just the right size for us to fathom them. But for an alien, maybe all my book is just one letter in an alphabet that, you know, with which they express truths of which we have no understanding whatsoever. So yeah, the difference between truth and certainty. I think we're all seekers of truth. We seek truth here in the Tai Chi practice, I think, and my hope is that somehow the truths of mathematics can be inspiring for many paths. But if you read the first chapter and I have the concept of truth. Well, truth is the zero, no, is one, and the false is zero. So we have 0 and 1. It's just two words, and it's certainly not what we seek when we say we seek truth. It will probably be a bit disappointing to just relate to this formal logic there, but it's the basis for a quest of much greater magnitude, and I think it can be. But if nothing else, it's a good training in certainty and just achieving certainty on certain things.
Maybe truth is beautiful and fun, like you said. That's
beautiful, fun, and participating in the divine harmony.
I think we're approaching the 1 hour mark, but I would like you to say something about freedom and constraint in mathematics, and maybe in Tai Chi.
Yeah. So I think the reproach to mathematics is that it's a set of rules, and you have to face these rules, and they are too strict, and it's contrary to life. Whereas the experience you have as a mathematician is that all these rules are some kind of ground on which you stand, and you can move around and create things. You create things, you make arguments back and forth, and so the end of this is a great feeling of freedom, actually. Funnily enough.
But most people want only freedom and no restriction or no constraint.
Yeah, you have to be prepared to submit yourself to quite strong constraints in this game.
It's tempting to make the parallel to music from the old Greeks, where you had the dichotomy, I think you say, between Apollon on one side and then Dionysus on the other side. And whereas Apollon was representing order, correct me if I'm wrong, then Dionysus was representing chaos somehow, and it was the interaction that created maybe the space where music can arise. So from music, if there is too much restriction, maybe you don't have the freedom to become creative. But if there is too much freedom, on some level there is no recognition, there is no narrative perhaps in what you're doing. Just from my personal experience, do you think that there is some connection to mathematics in this?
Yeah, I think mathematics is also just at the point of equilibrium between order and chaos, and that point of equilibrium we see it also. I would say in life. I mean, life happens just at the interface, I would say, and it's more than a funny pattern. It's quite unfathomable. But I don't know what to say about this great fact of life, that somehow things are not so chaotic that you have nothing to stand on, and they're not so orderly that it becomes rigid. And this meeting point is exactly the origin. It's in other origin myths. It's in the Nordic origin myths, where we have the meeting of ice, which I interpreted as perfect order, with fire, which I interpret as chaos. And at this meeting point, what is given birth to is a holy cow. So that's the miracle.
It's tempting to make the connection to yin yang somehow, where you have this. If you looked at viewed from like a conceptual distance, you have these two entities that somehow give life to one another.
Yeah.
So there is no freedom without the constraint somehow. My father used to say this, and I didn't believe him, but actually I think probably he was right somehow. And so I feel it brings us back to Taiji somehow. I'm not asking you to define yin or yang or the interaction of those, but isn't there something in the interplay with these opposites that make things interesting?
Yeah, I think it's interesting that in math, well, the way things are presented here, at least, we are able to just start from the concept of true and untrue, and that's the basic separation. And this separation somehow gets entangled with itself in mysterious ways that are creative.
Okay, I think we hit the 1 hour mark.
All right.
Should we? I'm not sure if we mentioned, but we would like to open up for questions. If anyone has something to ask the professor, this is the time.
I have one more poem, actually. One more poem, if I can remember this one. Okay. Yeah, it's in Norwegian too. And it uses some mathematical concepts, so just hang along. Og matematikk er et tempel hvor levende mønstre iblant slipper ut fortumlende ord. Mennesket vandrer der i en skog av symboler som iakttar det med nysgjerrige øyne. Slik ekko langveisfra sammenfiltres i en mørk, dyp og trolsk enhet, vi som natten og den gyllene klarhet, vil logikk, mengder og tall forløse rommet. Det finnes strukturer, urokkelige som fjell, smidige som elver, skarpe som solstråler, og andre, intrikate, fortryllende og triumferende. Rike brer de ut uendelige grener, mens kvantorer, konnektiver og deduksjon synger geometrien og sjelens rus.
So, any questions?
You mentioned that when you were a lot involved in mathematics, you sort of forgot a bit about your body. And then later on, maybe more were connected to your intuition and the heart. I wanted to know in which way the practice of Tai Chi sort of reconnected you to the heart. Has you, in a noticeable way, after years of practicing Tai Chi, been maybe going back home and being more inspired and ready to fill that empty space that you had created?
Revealing question. I think my realizing that there is a certain flow in the body connects with the feeling of flow in mathematics. For me, yeah, I think that has become clear. I don't think about mathematics when I do Tai Chi here. But yeah, the intelligence of the body is something I feel we are losing because it's quite funny. I mean, in first grade now, the students get the iPad, then they get the computer in the high school, but when they come to me, they get pen and paper. And I really believe in this hand-eye coordination, that you write mathematics with your hand, and there's an intelligence of the body that somehow the hand remembers what it has written, and this knowledge is stored somewhere. And yeah, there are many changes like that. And the other change was that geometry, the oldest of the mathematical topics, was excluded or very strongly reduced in the high school curriculum. And geometry was precisely where we learned the coordination of what you see in a figure and what you can deduce about the figure with language. So this was the hand-eye coordination that was taught for 2,000 years, and now for some reason, let's try something else. Let's look for funny patterns.
Anyone else has something to ask?
Yeah, I just wondered about this thing within infinities, that there are some mathematicians that don't accept most of the classical mathematics. They say it must be based on that things should not be infinite. They started historically with one that I just read for many years ago called Brevier, and then they have a field of constructivistic mathematics, and they have seen in the beginning they were not able to do very much things, but now they seems to able to do a lot of these things, and then you get rid of Gödel and all these problems. Do you have some thoughts about that?
Well, at the time of Gödel, there were very strong opinions for and against the different logical systems, and it was a very intense debate. Whereas now, I have the impression that everybody is allowed to do what they see most fit, and the different conceptions live side by side actually in mathematics. So the one you described is certainly not mainstream, but it's probably accepted.
One last question.
Oh,
perhaps you could tell us something about how you, or taste in mathematics, how to ask the right questions. Because one can certainly ask a lot of questions, and many of them are seemingly absurd. For instance, you could ask such questions as, is what I proved yesterday still true today? And the only way you can check is, well, wait and see. And you can ask that question for the future as well. Is what you prove today true tomorrow? Is your argument still an argument tomorrow? And the only way you can see is to, well, live tomorrow and check. Again, you can't prove it today. So there is a game of asking the right questions as well. Perhaps you can tell us something about your process in that regard.
yeah. So when you in the beginning of your question, when you asked about taste, my connections was with this sense of beauty and the aesthetics, and I just want to say it one more time then for myself, for everybody, that I think mathematics is somehow the combination of an aesthetic sense and the linguistic take on that. But then the taste. Then I want to say something about taste in general in mathematics. I think we agree to a large extent on what is beautiful, but I think it's no longer current dogma to say that certain things are beautiful. I mean, everybody is allowed to have their taste. We can perhaps hope to refine that taste or open the eyes of practitioners to certain things we think are beautiful. And this is I have linked this aesthetic sense to vision, but when you link by what you think is really interesting or what is somehow where the good stuff is, it's even more basic. It's the smell or the taste of something. That's perhaps the analog sensory system that is triggered. So anyway, my sense of taste in mathematics is just based on reading lots of stuff. For the question you asked about did what I proved yesterday is it still true today? I actually feel a bit fortunate that I don't ask myself this question. I don't think I'm a fast mathematician in any sense, but when I have proved something, I don't have any doubt about it afterwards, actually. Which can turn out wrong.
So did you say, maybe I didn't catch the point, but did you now say that the basis for choosing the questions was this aesthetic sense? Or
Yeah, that's a guide, yes.
Mm.
Yeah, but there is something more of the sense of. I think the Italians, at least, they say it's a nose, no? It's you follow your nose when it's when the meal smells good, or so somehow that's the symbol for intuition.
great question. Okay. Thank you, Snorre. Thank you so much. So,
Thank you for interesting questions and stimulating talk. And
I could go on, but I mean, we had 1 hour, so. All right. What are we going to do now?
Well, thank you. I thought we could do some of these funny moves. Talk about divine energy and funny moves. So, one-on-one is fun. One-on-one is fun. Yin and yang. We could go out with a bang if you want. Let's do some pushing moves. So here we have yin and yang. Are you calculating what's happening now, Professor?
There's a simulation going on somewhere.
So you said you never do mathematics when you come to Tai Chi. I do it all the time. I'm calculating everything that's going on with my whole being. So welcome to my class. And you will continue to be welcome. I've thoroughly enjoyed the evening. I would be a liar if I said I understood everything. But I have something for you. As I mentioned to you, 24 hours ago, I visited the Science Museum in London. I calculated this moment extremely well in my life to arrive at this particular moment. As it is, the Tao is always with us. So, when I walked through the mathematics department of the Science Museum, I came into a little shop and I found what I think it could be the answer to too much mind. As I found, lo and behold, there's too much here, as usual. I found some equations. So I don't know, perhaps it's a possibility that that these equations, which start all the way up here somewhere, could ground you. Fit.
Okay.
Yeah, I've also got one feeling.
Thank you.
I love these great coincidences.
I also want to give you something.
Oh, me? All right. I haven't finished yet, but The Science of the Mind. Okay, what size are you?
42, 43.
Oh, yeah, the answer to the universe, huh? 42. Ooh. It's exciting.
Some weeks ago, I discovered we have an interest in Hafiz. And anyway, at one point he says, if it's not a romance, then what is it?
Oh, wow, Hafiz, fantastic. Thank you. Thank you.
And Lars, there are some other good books in mathematics. I found one. Here's one I like very much.
Thank you. Lots of sir. Thank you very much.
Thank you so much. It's the gift by Hafiz, a great Sufi poet. Thanks. So I haven't quite finished. So there's one more thing actually. Yeah. So I found a great guy. You might recognize him. Albert Einstein. So, as you're quite a mug, I bought you a mug. It's a math mug. And, of course, what does it say here? Pure mathematics is in its way the poetry of logical ideas.
Not bad, not bad.
So I'll open it up so you can all see it. And of course it is, from this moment, almost empty. There we are. Now it's empty. So I hope you continue to have it empty.
Okay,
And you can keep studying as long as cows come along. Must be a holy cow somewhere in there.
Thank you so much.
So for the emptiness. Thanks for Yeah, so now there was going to be something unusual. Shall we?
Sure.
Okay, so this is a little surprise, impromptu. Nothing too calculated about this. The formlessness of form is what we're going to enter into, make this a very, I would say, call this a logical conclusion to the evening. We need a logical conclusion to the evening. Please enjoy. now I would like to invite you all for some Tai Chi punch. Have a drink and enjoy the evening together, and we have some snacks, bits and pieces. The professor's been chopping and cutting all afternoon. Slave labour there, got him working hard. So please don't let it all go to waste. Enjoy and have a little mingle, especially if you're single. And welcome back.
And if you want, you can buy my book. There's no pressure. Actually, I know that one person has bought my book because I got an email today about with somebody pointing out a mistake.
That was probably the poetry, though. So there's going to be some book signing in the back of the room, actually. If you've bought his pen.